All right, so till the last time we have learned about the recurrent neural network. Let me just go over the agenda quickly. So, all right. So far what we have learned is, all right, the use cases of recurrent neural network. So essentially it is good for doing the predictions, specifically those that involve sequence or a particular order. All right. So in this, we basically um, feed the previous steps of uh, feed the previous steps output back as input. That was the core, and we can put multiple such neurons together and to make it more robust. All right. So this is what we discussed. This is how it works. This is, let me make it full screen quickly. All right. So what we learned till last time was the basics and foundations of recurrent neural network. Recurrent neural networks are very popular and are used very often when it comes to text processing and other predictions such as the time series predictions. All right. So So we talked about these parts where the recurrent neural network can also work like, can also ignore outputs and also can skip the inputs. And such a combination is generally called encoder and decoder. We will talk about this kind of format when we do the language translation. And it is basically a combination of two networks. Then Then we talked about, we tried to build a RNN using TensorFlow. This was the first attempt where we were using our own way. And then we used the static unrolling, whereby the inputs were predefined as input size, and the input was defined as an array. And then we created the RNN using the dynamic RNN function. So, right, and afterwards, so we basically learned how to use the dynamic underscore RNN, and the core idea was that we were first creating a cell and then using the dynamic RNN over on top of it. Okay, so we'll see that there are many kind of many kind of cells, not only basic. There is one LSTM, there is one GRU, and so on. All right, so we'll learn that part. Afterwards, basically we learned about how to handle the variable length inputs in case of dynamic RNN, because not all inputs are the same size. Specifically, you will notice that when we do the complex things like language translation or even say audio processing, the input may not be of same size. All right. So here we talked about that we could put a end of line marker, and then those inputs will not be processed after that point. All right, so yes. Then we learned about how does the training work. So training an RNN involves essentially the same thing as what was involved earlier, which is backpropagation. So if these were the inputs, here, and we are getting certain output here, so we can back propagate the errors and find out the value of W. Okay, so that's what we discussed till the last time. All right, and then we trained the RNN to classify MNIST images. That was the basic example, though the performance may not be as good as CNN, but this was basically the hello world of any machine learning program. Okay, then we talked about training to predict the time series. All right, so this is where we were. All right, so yeah, we were here. So we were starting with training a sequential classifier. Here we will go over the whole structure of the program, and then we'll take a look at the output. All right, so let's open our notebook. You can pull it. Let me also, although I put recently. All right. So let's go back to our notebook. Okay. So in this notebook, when you open it, you need to run the include section, this part, and then the import TensorFlow. All right. Then we can scroll down to the point. Yeah. All right. So till this point, we have discussed already. Yeah. All right. So let's go over the code and try to understand what does it mean. So initially, we are defining the how many number of steps do we want, how many number of inputs do we want. Okay. So what we are feeding this classifier is that we are feeding 28 pixels at a time. Okay, and therefore there are going to be, we are feeding 28 pixels at a time, and we are going to have total number of 28 steps. Okay, so our x that you see here is a three-dimensional vector whereby the first dimension represents how many instances are going to be there, all right, that we have left as open. Then the second dimension is number of steps. The third dimension is the number of input features. Okay, so for each batch or for each input batch, there are going to be n number of steps and so on. So it is essentially we are feeding one image at a time, and we are unrolling it into 28 steps. Okay, and the y is going to be again it is going to be a single dimension vector with many instances. So here we have left it dynamic. Okay, so we'll be feeding this part. This is going to be 0, 1, 2, and so on. All right. Now, yeah, number of neurons in each layer. Thank you for asking that question, Vidya. Number of neurons in each layer is how many neurons are going to be in each cell. I'll go back here. So here, this is the architecture of this. Mm, this is the architecture of the MNIST classifier. So what we are going to do is we are going to have 28 uh, 28 unrolled stages, as in this is one, this is another, and so on. So it is going to be having 28 steps. So we'll feed first pixel, then second, and then so on. So we're going to essentially have 28 steps in the recurrent neural network. So this is what it shows. And each of the step, at each step, we're going to have inside this, there are 150 neurons. So this architecture would make more sense to you. Okay, let me just show you that part where we discussed that. All right. So this one, right? So we talked about a single node earlier, but single neuron, but here there are many neurons, right? It's a layer of recurrent neurons. So this whole layer acts like a single neuron. So these are 150, right? So these are 150. So each individual cell has 150 neurons. All right. Okay. So we'll treat each image as a sequence of 28 row by 28 pixels. And we will use 150 recurrent neurons plus a fully connected layer of 10 neurons, one per class, connected to the output. So, and that will be followed by a softmax layer. So we'll have here, this is how it's going to be. They're going to be 28 step. And at this point, we will have fully connected units. The whole thing is connected to to dense or fully connected neural network, which will take the input from here and then feed it to the softmax. Softmax is the one which is going to compare it with output afterwards. All right. So this is what's going on here. Now, so you have first of all, we are defining the basic RNN cell with these many neurons. Each cell that you saw in the diagram, each cell that you saw, this is known as the basic RNN cell. All right. And here we are specifying that create basic RNN cell with these many neurons inside it. Then we are creating a dynamic RNN using this cell factory. This behaves like a cell factory, with using which we can create any kind of complex structure. Okay. So in whatever way we want to arrange, you will see later that we will use this and this is basically the dynamic unrolling part, whereby we're feeding the input back and so on from the same cell. All right. A question from Vinta is a fully connected layer. What does it mean by fully connected layer? Good question. So fully connected layer means whatever we learned earlier before CNN, whereby you have a bunch of neurons, we're feeding the input to them and so on. That is fully connected, a linear list of neurons. All right, the standard one. All right. So basically, the fully connected essentially means the you have a bunch of neurons. We have feeding the data to them, and we're getting output from them. So that's basically the fully connected. So as we learned earlier, also even in the complex structures, we whenever we want to do one more layer of um, predictions or one more layer of figuring out the figuring out the output, we generally put one more layer of fully connected. Okay, so the same is here. We are the output of RNN is being passed to a normal neural network. Okay, that's what is happening here. So once we have created the dynamic RNN, we get two things. One is output from each of the stages, and the second one is the final output of the whole whole neural network. Okay, so this is from the each stage, and this one is from the overall, right? Afterwards, here we are feeding. You can see that this is the factory with which we are going to create, and then we are feeding X to it, and then here the logits, the last after the dynamic RNN, we are feeding it to the normal fully connected network. We created our function called fully connected earlier, but now the TensorFlow already has a function called tf.layers.dense, using which we can create very easily the layers of network. Okay. All right. So a question here is, what does it mean by the cell here? The cell is the one, that individual entity, where we are. Cell is essentially like a factory with which we can create the whole neural network. So this cell is what is going to be repeated. This cell is what is going to be fed data to, and this cell is what we are going to do the back propagation on. So this cell is something like, you can think of the way we create a class and then we use its objects. In the same way, we're constructing a basic cell, and using this cell, the dynamic RNN is creating the entire structure. All right. So you can think of the RNN cell as like a blueprint or a factory with which we could create many instances of the cell, and we can arrange them. We can arrange them in all kinds of sequences. All right. So similarly, there you can extend the basic RNN cell. If you don't like the basic structure, you want it to feed more number of inputs and so on, or you think that instead of having one layer of internal neurons, if we had two layer of internal neurons, so you could construct your own basic RNN cell, and then feed that to dynamic RNN. All right. Good question. So next question is, I think it's good that the Vidya is asking these questions, because it's important to important to refresh it. So a question from Bidda is, what is the difference between dynamic RNN and static RNN? All right. So in case of static RNN, we knew that our input sequence was fixed, and we knew exactly upfront at the time of constructing the network how many how many uh, how many inputs are going to be there, what inputs are going to be there as an array, right? So that was basically the case with the static RNN, but that's not possible in practicality. Therefore, we have dynamic RNN. In dynamic RNN, we do not need to know upfront that what are going to be our inputs. We just need to define the structure. Okay. So in case of static RNN, we needed to pass an array of inputs. We needed to pass an array of inputs, and here we can we're passing the input as a vector, or you can say that we're passing the input as a matrix. So that was the difference. All right. So once we have created the dynamic RNN, we get the outcome. This is the overall outcome, and this is the outputs at every stage, right? So at every stage, what does it mean? So all of these stages, like x0 will give some output, x1 will give some output, and so on. And finally, when we have fed all the 28 pixels, then we will get the final result also. Final result is same as the stage, the answer from the last stage, right? That you can always compare. So outputs and states basically states is the last value of the outputs actually. Okay, so but in here you can see the next layer is fed the outcome of the overall outcome, or you can say the overall state of the dynamic RNN. You can see that. So we are creating the dense layer or fully connected layer of the neurons with the inputs from the previous layer and number of outputs. How many are the number of outputs? 10, because we are doing the MNIST, and therefore the outcome is going to be somewhere between 0 to 10, including 0 and 10. All right. So this is the outcome of the network, and then we are converting that into probabilities here after normalizing. And okay, so this is cross entropy. Cross entropy shows that how far are we from input. So here we are passing the labels, as well as this is the predicted result. This is the actual result. And this one is going to first convert the outcome of the fully connected network or dense network into probabilities, and then it will compare the probabilities with the actual values and then give you the distance. This is the measure of the distance, that how different is the output from what we were expecting. Okay, and then we are summing it up. Okay, we are computing the mean after summing it up, and then this is our loss function. So we need to minimize this loss function. And here we are using an optimizer such as Adam optimizer. Okay, so using this optimizer, we are going to minimize the loss. Using this optimizer, we are going to minimize the loss. Okay. Afterwards, here, so this is the training up. So now this is the one that we are going to run it again and again and feed more and more data every time. So also here we are trying to print the accuracy by by comparing it if this exists in top n number of outcomes. Okay, so a question from Bintao is that is sparse softmax cross entropy with logit. So it's essentially a combined composite function that first computes the softmax. What is softmax? Softmax essentially converts the numbers into the probabilities, right? And it's basically taking one value and dividing the sum of all the values, and not like this, but by putting e to the power something, e to the power the value, and then dividing by sum of e to the power all values, right? That was softmax. Softmax essentially converted the numbers into probabilities. All right. Then probabilities means it will be all the numbers will sum up to 0, and each value will be between 0 to 1. Okay, so that's what softmax does. And then what does cross entropy does? Cross entropy compares the actual input against what we were expecting, and then computes the loss. If your input is different from the expected output, this is going to be a big number. If your output is going to be similar to the going to be same as the output, then the resultant is going to be 0. Remember that we did y into log of something plus 1 minus y into log of something, right? This is that one. So cross entropy and softmax combined together is this function. Does it make sense to you? So softmax basically converts the outcome of fully connected network into probabilities, right? The way we used to normalize, in the same way the softmax does it. And cross entropy essentially compares each probability with the outcome expectation. And in case your outcome is not matching the expectation, then the resultant is going to be huge value. If your outcome is here, the outcome of the network is matching with the target or labels, then we are going to get 0 as the loss. All right, so that's what the cross entropy does. Good questions. And all right, now the next step here is that we are summing up all the losses for all the outcomes of this. Now next is here, created the optimizer, then we created the training operation, which is minimizing the loss. And then here, this is for printing the accuracy. Okay, so we are checking if the y, which is expected value, exists in the logits in top 1. Okay, the probabilities, because this is what it is. So here, logits is going to be the list of probabilities, and we are saying that so logits is a probability, is an array of 10 values. Logits is an array of 10 values showing the probability of this input being 1, the input being 2, input being 3, input being 4, and so on up to 10. So logits is basically the probability that a particular input belong to each one of 0 to 10, right? So we are saying that if y, the expected value, is in the highest probability here, that's what in top k does. Here we are saying in top 1. Okay, so if the expected outcome has the highest probability in logits, then this basically returns a Boolean flag. Okay. And since it's going to be called on the list of values, therefore the here at this point, the accuracy is going to be the average of all the correct values. Okay, so that's what we are saying, that mean of all the correct values is going to be the accuracy. Okay, here we are converting this Boolean flag into a float number. Okay, what I understand it, let me just check if, okay, so let me just show you this function again. All right, so here it returns a Boolean, you see, it is a Boolean one. Therefore, we need to cast it to integers or floats. That's why we are converting into floats. Why? Because you want to take the average of all the values. Okay, and hence we are casting it, and afterwards here we are computing the mean of all of these. Okay, so this is for printing. Every time when we move in a step, we are going to print the accuracy. Okay, casting means converting Boolean into integers, right? So, okay, those who are not from, let me just show you what I mean. Okay, so somewhere like here, it's going to be, let's say, okay, let me go back. Okay, so it's going to be a matrix of, say, probabilities. Okay, okay, so here basically when we are saying logits, right? Logits would look like this. Each logits will be having 10 values, 0 to 10. Okay, and for every instance it's going to be a bunch of values. Okay, so here, so these are for each instances that we are feeding it, the whole of it. And here this is going to be, say, probability of input being 1 is, say, 0.8, and probability of input being 1 as 0.6, a probability of 2 being zero point 0.1, and so on up to 10, up to 9, not 10. It's going to be up to 9. And then here we are saying, so in top K, when we are saying our output is say actually output is 0, right? So in top K, what's going to do is it's going to find the max of these probabilities and check if 0 belongs to the one that has highest probability. So it is going to give us true or false. Okay, so this will get converted into 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 a vector of true and false, right? True and false, right? So similarly, there'll be 10 more probabilities here, and it'll be comparing with some actual label and so on, right? So it'll get converted into this kind of array, right? So now at this point, we need to find the accuracy of each patch, right? So what we need to do is we need to find out how many were true, how many were false, and so on. Therefore, we need to cast it into zeros and ones, right? That's what we're doing here. So this will become true, will become 1, this is 0, this is 1, and so on. So unlike C, in C we used to simply use the 0 and 1 as true and false. Here we need to explicitly cast cast true to 1 and false to 0. This is what casting does. Okay. And afterwards, when we are computing the accuracy, this will be summed up, all of these, as in all of these will be summed up and divided by the total value, total numbers. Okay. So sum of it divided by the reduced mean is sum of it divided by n. That is the accuracy. All right. That's what we are doing here. Okay. Great. Great. Thank you, Gigi. Yes. So casting means forcefully putting something into a box or into a certain other shape than it was actually. Okay, so that's what is happening here, and once we have the accuracy, we can print that how well is our network doing at every step. Great. Then we are loading the data. We are loading the input data from of MNIST. Let me run it. Then afterwards, we are reading the data set, and we are creating X test and Y test. Okay. Okay. So here note that we are reshaping this batch. Okay. Just to understand this portion, let's try to understand what exactly is going on at this stage. Okay. What exactly is going on at this stage? Let's say our batch size is, say, 2 records at a time. We want 2 records at a time. Okay. And here we are saying, we are asking MNIST to give us the next batch. Okay. So let's take a look at both, or maybe just, okay. So here we are saying, okay, so let's take a look at X batch. Okay, so it doesn't look like very great, so we'll have to, okay, so this is 28 by 28 pixel. Okay, so this is, there are 2 records. This is one image. This is another image. Okay, and if you take a look at this one and we say length of this, right, it should be 28 into 28. That's right. So X, each instance, X batch is nothing but nothing but bunch of bunch of images as array. Okay, so each row represents all of the pixels of the images, right? Next is Y batch. Y batch is right. Y batch is basically the outcome target or label, whereby we are saying that first record of X. Okay, so this image represents 8 and this image represents 5. That's what it means. Okay, and now at this point, what we are trying to do is we are reshaping X batch. We are converting X batch into these many inputs, these many steps, and these many inputs. Okay. Now let's take a look at it. All right, because we need to feed 28 pixels out of it at a time. Okay, and we have to feed it 28 times. All right, that's why we are reshaping it. and let me show you how does Reshape looks like. Reshape is looking like this. Okay, so in this, if you see the length of Reshaped, as in number of rows are going to be how many? The number of rows are going to be the 2. Why? Because that is the batch size that we have taken. So each image here is going to be broken down into two parts, as in two-dimensional vector. All right. So if you take a look at, say, 0th element of this one, it's basically 28. And if you take further look at it, so that is 28. So the dimension of, okay, so let me show you the, okay. So here it is a three-dimensional vector. Okay. So reshaping this means converting this two-dimensional vector into three dimension such that the first one is basically whatever is there, and second part, basically this part, the each row is being broken down into number of steps like this. Okay, while first axis will remain as such. All right. So here we are just demonstrating the with the batch size of 2, but the batch size here is 150. So this that you see here, let me just change it. Okay. So here that you see here, okay. So this is one image from here till here. This is one image. This is another image. So there are two batches right now. Each batch contains one image. Each image here is basically is composed of total number of inputs to the each of the neurons, and here we're feeding. So basically this is, there are 28 steps, and at each steps there are 28 steps, 28 sequences, because in RNN we can feed multiple inputs, right? We'll have to feed multiple inputs there. So there are 28 unrolled stages, and in each stage we are feeding 28 pixel to 28 inputs. All right, that's what is going on here. A question from Vidya is, what is size shape of X batch? I hope this is clear now. Here at this stage, when we loaded the data from the MNIST, the X batch was a two-dimensional vector. Okay, each row representing one image, while here, we have reshaped it into three-dimensional. Okay, such that each row was broken down into 28 steps, and 28 inputs, the number of input features. All right, great. So at this point, we can start the training. I'll just decrease the number of epochs. Say I'll change it to say 30, and then see the result. All right, is it working? I hope I was able to answer your question, Vidya. All right. Okay, so this is the accuracy in the first step. It's going to take a while. All right. So in the meantime, let it run for some time and then you can continue our discussion. All right. So this part we have talked about. All right. So with around the total number of epochs as 100, we can achieve about 98% of accuracy. Okay. So that's not bad at all. Okay. So we could get better results by tuning the hyperparameters and initializing the RNN weights using he initialization and training longer, or adding a bit of regularization such as dropout. Okay, so this we can do on RNN. We can further improve it by the same thing that we learned earlier, in the training neural network, whereby we could tune the hyperparameters such as number of neurons we want and number of unrolled stages and the RNN weight initialization also we could choose from others, and then we can train for longer, maybe more number of epochs, and we could do a bit of regularization such as using a dropout layer. All right, so okay, now let's train the RNN to predict the next value in generated time series. Okay, so we are going to generate artificial data, and then on that artificial data, we are going to see if our RNN is able to predict that, right? This is very much like a stock prediction algorithm. And instead of getting the actually stocks data, we are creating the data. We are using the mathematical formula to create it. All right. So each training instance is randomly selected sequence of 20 consecutive values from the time series. And the target sequence is the same as the input sequence, except it is shifted by one step into the future. So let me show you what it means. Here, what we have done is using this formula, we have created this time series. This is something an RNN can fit, but a linear regression cannot fit. Okay, so this data is generated using t dot t into sine of t by 3 plus 2 into sine of 5t. So this is what it looks like. And so here, what we are going to do is we are going to say take 20 values from it, 20 values from it, and and we're going to observe the outcome of this one. We're going to see what kind of output do we get after feeding these 20 values. Okay, that's the prediction. So we are going to feed it and then observe that whether RNN is able to predict the next values. And once we predict it, and you can see here, this is the outcome here. It is showing that the asterisk means the target, the actual, and the the blue one, the blue large dot is the predictions. So you can see here, this is what we are going to achieve. Okay, so let me just okay, let's just get started. So construction phase, what we're going to do is we're going to have a neural network with 100 recurrent neurons, and we'll unroll it over 20 time steps, since each training instance will be 20 inputs long. Okay, so So we're going to have a sequence of 20 being fed to our RNN, and each time each input will contain only one feature, the value at that time. The targets are also sequences of 20 inputs, each containing a single value. All right, so this is what it looks like. It is still running. Should I interrupt it? That's not a bad accuracy for 9 steps. Okay. All right, so let me just check what happened to the multi-layer one. Just give me a second. I want to see multi-layer should be after this or before this. Yeah. Okay. We're going to have multi-layer later. All right. So here, this is what we are going to achieve, and we'll come back to this one again. All right. So here, first of all, let's take a look at this function. This is the time series. Given a time, it generates the some value. Okay, and then in the next batch is nothing but going over the time series, is generating the random values for time, and then in a certain range, and then it's basically generating the y value and giving it out after reshaping it. Okay, converting it into 2 dimensions. Okay, it's converting into 3 dimensions actually. Okay, so let's take a look at how does next batch look like. Okay, so we're saying give me say 10 records, or say give me just 2 records and say 4 number steps. So you can see. So this is what it gives us. It gives us uh, it gives us a 3-dimensional vector whereby from here till here. Okay, so you can see from here. Okay, let me just show you properly. This is the whole batch, and the batch looks like this. Okay, so length of batch is the total number of rows are going to be 2 in this, and the, let's say, 0th row in this batch is basically of 4 records. Okay, so this one is basically the 4 records. All right. All right. So it's essentially we've broken it down into the number of instances we are going to feed and the number of sequences that we are going to generate at every point. Okay. So that's what it is. And moving ahead. So here we are trying to generate the timeline, okay, the timeline, and in the total number of space, and we are this one is for generating for only a small part, and I think the output will be more interesting. So so this is what we are trying to generate. So this is our generated data, which we just did. Okay, so this is our generated data, and we have just plotted that data. Okay, we are calling here time series, and here also we are calling time series. All right, so all right, now we can test it out. How does X batch, Y batch looks like, and we could, all right, for yeah, for this value we have this and so on. Okay, so so far we have generated the outcome at this point. Now let's create an RNN. It'll contain 100 recurrent neurons, and we will unroll it 20 time steps, since each training instance will be 20 inputs long. Okay. All right. A question from Vinta is, what is R function in the label this? Okay. So, okay. Here, right? Here we want to, okay. Is it the color? I don't know. Actually, the here, see, dollar generally means here, dollar generally means it's a, it's a italic. Okay. And R is, I think, R is, I think, for the raw string, we call it. This is for raw string in Python. And we are passing that raw string to as a label to display it here. Okay, great, great. Uh, There's basically a format for feeding the label value so that we can display it here. So R represents the raw string. Okay. Okay, moving ahead. Now, at each timestamp, we now have an output vector size of 100. Okay. So if you think about it, okay, let's give it a shot. We have already shown this one, right? See, you've concatenated the columns that you want. Yes, go ahead. Can you try C for column? All right. So this is for concatenating these two columns together. That's what it is. Mm-hmm. All right. Sorry. So Binta's question is that if we try C here, will it work? No. It means R represents raw. Okay, R represents raw. Okay, so a Python string starting with R. Okay, okay. R means the string will be treated as the raw. Okay. So the raw strings could have their own way of dealing with slashes and so on. So that's why. All right. I hope that's clear. This R for RAW. All right. Maybe the pronunciation is not clear. And all right. So move ahead and let's start training it. Here there's one bit of extra information that we need to know, that at every step we now have an output vector of size 100. Why? Because we have total number of neurons as 100. Okay, so we are creating a basic RNN cell. We are creating a basic RNN cell with number of neurons as this. Here we are using ReLU as activation. And to this dynamic RNN, we are feeding the inputs. And in each of the stages, we are we feeding in each of the steps, we are just feeding one pixel at a time, right? The number of features in our input data is just one feature. Okay, but the number of neurons that we have chosen are 100. Okay, the number of neurons that we have chosen are 100. That means they're going to be 100 outputs out of this dynamic RNN cell. Okay, they're going to be 100 outputs for every pixel. That's what it means by having 100 neurons. And therefore, we need to collect it and consume it. Okay, collect it and then convert it into maybe 0. So at each step, we now have an output vector of size 100 because every step we have 100 neurons. Okay, but we want a single output value at each time step, and so what we do is there's something called output projection wrapper. Okay, so a cell wrapper acts like a normal cell, proxying every method call to an underlying cell. Proxying meaning whenever somebody is making a call to a projected cell, it'll basically call the underlying method, and it can also add some functionality from its own side. So output projection wrapper cell is basically it adds a fully connected layer of linear neurons without any activation function on top of each output. Okay, but it does not affect the cell's state. All right, and all these fully connected layers share the same trainable weights and biases. Okay, so essentially what we are doing is we are converting these 100 neurons into further lower, like 10, and then using those further. So that's what is going on here. So what's happening here is this was our actual cell. This was our actual cell, and this was our basic RNN cell. On top of it, we have put one wrapper. This one is going to give us 100. This one has 100 neurons in it. Each pixel that is being fed is going to 100 neurons, and those 100 neurons are giving 100 outputs. And this fully connected unit that we have put here is going to combine those 100 values and going to give us 10 values at a time. Okay, that's what the purpose of purpose of this output connection wrapper. Okay, so the output wrapper is output projection wrapper does the same thing. Okay, so here it should be output projection wrapper, not connection wrapper. All right. So wrapping is quite easy. Just create another class called output projection wrapper. Pass the object of basic RNN cell, and then pass the object of the basic RNN cell the way we did earlier. And here we could explicitly specify how many output size do we want. Okay. So let me go back to the code here. All right. So here is this part. So this is clear, right? So here we are. Okay. I think this we can ignore because we're going to create it again. So reset graph is clear, number of steps are clear, number of inputs, we are saying there is only one input feature called particular value there, the value of y, the stock value, and number of neurons in each basic unit are 100. Number of outputs from the each neuron, each expectation is only one. And here, this is what we are passing. So we are passing, say, 20 values at a time, having only one feature. Okay. So this is 1, this is 20, and this is this could be batch of any value. Next is the y. Y is similar to x, similar to x. Okay. For every batch, the next value is what is the result we are expecting. Okay, and here coming down. All right, so this is where we are using the output projection wrapper. This is our basic class. Okay, this is our basic class, you can see till here. And this is the basic class. And we are wrapping it in the output projection wrapper. Now we'll use this with dynamic RNN. Okay, this is our cell that we've created. Then we are going to use this cell with the dynamic RNN. All right. So, and this is the outcome, and this is the output from each sequential step. And this is the outcome of the overall steps when we have done feeding all the steps. And then we are going to basically compare the outputs with the y. Okay. Here, please note that we are comparing the output at every stage. So we feed the data, we feed one value, get one output, we compare it with expected output. Okay. Okay. So question is X 4-dimension? No, X is 3-dimension, you can see. All right. So here at this point, this is our loss. Loss is nothing but what was the expected value of the stock and what is the actual one. We subtract that and we square it. Okay. The outputs is basically the outputs of this one is going to be basically array, or you can say vector, and vector having the same shape as this one. Okay, as y. All right. So yeah. So the output is going to be having number of batches as well as number of steps and number of outputs. input, that is the dimension. All right, and then once we compute the loss, here we feed it to the optimizer to minimize the loss, and this is the one that we are going to train and optimize. All right, so let me run it. All right. A question from Minta is, by my memory, X was a four-dimensional vector in the previous case. Why? Let me just walk you through that. Right. Okay. So let's just go back here. All right. I'll have to, yeah, because we had discussed earlier that. Okay. So where is my, yeah. So yeah, I'm just trying to figure out. We did discuss four-dimension vector. Yeah, I'm going to take that. All right. I'll have to, yeah, go back to the point where we discussed. We did discuss four-dimensional vector, and the fourth dimension was one was the number of instances, right? And okay, I get it. So basically, if we have the data, if you take a look at it, yeah, I'll just explain to you what it means by fourth dimension in it. All right. So fourth dimension means the number of batches is the fourth dimension. Okay. Number of batches. Right now, one is number of batches, then number of instances in each batch, then how many input features are there, and then how many sequences are there, and then how many input features are there. That's the fourth dimension was the number of batches. Okay. I hope, yeah, yeah. I think that was it. Correct? I'll take a look at it again. We did discuss like four dimension. The four dimension was the number of batches probably. All right. All right. So this is what we discussed. Now let's go back and execute the part where we were. All right. So we were here. Great. Great. Moving ahead. So right? This one was what we're discussing. So this is clear that the X is number of instances per batch, and this is the number of steps in the for each instance, and for 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 each of the record, and here the number of input the features. All right, so we created the output projection wrapper on top of basic RNN cell, and then we created the dynamic RNN here. So basically here we are feeding the individual cell to it, and we're feeding the data to it, and we are specifying the data type. All right. Next is that once we are here, then we create the optimization variable, the one that we're going to do the training on. Also, we create the saver, and so that we could save the session into a particular file or so. As a general thumb rule, we should be using the saver. Okay. So here you can see that the MSC is reducing. All right. So for every batch we are retrieving, there are 20 records that we're feeding to it. And for the outcome is again going to be 20 records. We're comparing with the Y batch. And then we are printing we are printing the mean square error here. Okay. All right. So the mean square error is quite low at this point of time. It's actually 0.04. And right. So we can at this point, whatever predictions we have right now available, so whatever session we have created, the model, we can reload it again. So here we are saying with tf.session as session, and we are saying saver.restore. Okay, so we are loading whatever we did here at this point. We're just reloading it just to show you that that once you save this, you can reload it at any point of time. Then this is the new. This was the expected, and this is the predicted value. Okay, so this is for this time series. Okay, so right. So this is what we are doing for comparing the results. Okay, let me just show you. Now you can see here we have plotted the uh, okay, so let me just okay, so we have plotted the actual versus prediction. Okay, here the Y predicted is red, you can see red, and it's a dot. Okay, and so we have here, you can see this is the predicted value as per our network, Y predicted, and this the one that you see asterisk with, that one is the actual value. So you can see the predicted one is very close to the actual one. Okay, predicted value is very close to the actual one. Okay, does it make sense to you? So all we did was we used this model to do the predictions. Okay, so here instead of doing the predictions here, after we let it train, and once it was trained, it has done the training for around 1500 steps. Then we saved the result into a file, and then we reloaded that session and computed the predictions for the new values. Okay, we fed the X new, and we predicted those values. Okay, so that's what we did here. And for this X new, All right. And once we are there, then we have tried to, let me see, are we using X new here? Okay. Yeah. So here, yeah, here basically we have tried to show it on the chart that how close are we with respect to the actual one. Okay. A question from Pratik is, what if there is no clear trend but some noise in the input time series? Okay. Yeah. So yes, a good question. You could give it a shot. I will suggest that you change the time series to probably put a random number here. Here, you could put a random number here. Okay, and then see then see it if it is able to give you still the good result. So it should be able to let me just use what was that function? Okay, so say np dot random dot, okay, so all right, what does it mean? All right, I'll just use this. Okay, so here I'm adding a tiny value. I'm not sure how does this much look like. So how much does the time series, let's say value of time series at 1 because it's going to be really tiny. Okay, okay, so I think what I have to do is probably use it something like this. All right, so yeah, let's just add some randomization to it. I think that would make okay, so right. This time there is a bit of, it's not that clear. Okay, so maybe we could have just divided by 2 or something. It still looks really nice graph. Okay, so now I have distorted the actual one with putting some random values. Okay, the random should not be just too random. Otherwise, it won't be able to figure out any pattern. Okay. Okay. So I put a tiny noise. I won't put a really huge noise. Okay. Still, the mean square error is actually similar. Okay. So yes. So you can see that still it is able to predict, but it is a little bit more off. Earlier it was very close to the actual data, but this time it is a little bit more off. Okay. So So yes, which is very natural that in case we have more random values there, then the chance of it being off is very high. All right. So yes, so we were able to plot the we were able to do the predictions on the stock market. Now you can actually plug it in on the real stock market and see if it is able to predict. Yes. So it will be able to do a pretty good job. You can try increasing number of neurons. You can try the you can try increasing number of neurons. You can try putting bigger sequence of data rather than 20. You can put the number of step size to be say 500. 500 will require a more memory and more time at every step. Okay, because this one is predicting the next values based on last 20 values. Okay, based on last 20 values, and you could make basically, if you increase the number of steps, the total time that takes to do the prediction will be little more, will be far more. Okay, because at every step the backpropagation has to compute all the values back till the 20th step in our case. So okay, that's why you could experiment with increasing number of steps. You can experiment with there are a couple of more ideas that you could try. That one of the data points, when you are feeding the stock data, what you can do is, let's say, not only the current values, say pick one value from every week, or say average of every week, or say average of every month, and so on. So plug in those values along with the data, then you will be able to carry over more. Okay, so let's go ahead and we learn some more great ideas about recurrent neural network, because RNN has been used for a lot of things other than a stock market, and there have been quite a few researches in this domain which we will go over. All right, so this was how you predict the time series. All right, this one we have done. So although the output projection wrapper is the simplest solution to reduce the dimensionality of RNN's output sequences down to just one value per timestamp per instance, but it is not the most efficient, right? There is a trickier but more efficient solution. We can reshape the RNN's output from batch size, number steps, and number of neurons to batch size into number of steps and neurons. Meaning, we gather we gather the we gather the result from all of the steps and kind of put it into a single list. Okay, so we could basically gather the result from each sequence and then connect that to a fully connected one. That's what we are doing here. So this is what we are taking, instead of just applying the fully connected network here and converting the 100 neurons value into say one. What we could do is we could gather all 100 values from all of these, and then using basically concatenate all the results and feed it to the feed it to the fully connected unit or dense unit. So here we could create another neural network and feed the data from each sequence and get the result here. Okay, so instead of every sequence, what we were doing is we were converting here there were 100 neurons, right? There were 100 neurons. So let me just draw it for you. Okay, so all right. Okay. All right. So let me just. Okay. Let me just show you what I mean. Okay. So here, right here, there were 1, 2, 3, 4, like this. There were 100 neurons, right? And when we were feeding one set of values to this one, there were one pixel that we were feeding, and that pixel was being fed to all these ones, right? All of these, all of these, and they were basically converting it and giving us the results. So there were 100 such values that were coming out. So what we did was we put a neural network on top of it and converted that into our desired value. That's what we did by putting the projection wrapper. Here, what we are doing is what we're doing is we are letting it give 100 values, each of them, and then converting them converting those 100 values into rows instead of columns. Okay, basically concatenating those values. This will contain 100, this will contain 100, and so on. And then we are feeding this after concatenating all of these values. The batch size will become multiple. Batch size will be multiplied by number of steps, because if 10 records came from here, 10 records came from here, and so on, and there were 20 batches, so 10 into 20 will become the total number of records here. Okay, total number of rows or total number of instances, you can say. And then we feed it like usual fully connected neuron, and and then we get the results. And then this is where we can do the comparison. Okay, so so we can reshape this. Basically here at this point of time, we are just converting all of the outputs from all the steps into a single array. Okay, so as and when more and more records are coming, so we feed these records to fully connected, then these, then these, then these, or we'll feed these instances to fully connected unit, these instances to fully connected unit, and so on. Okay, so here there will be 100 values coming as parallelly, then we convert them into something like instances, and then feed it to the neural network. So instead of using projections, this is another thing that we could do. And as and when more and more values are coming from all these, we are feeding more and more values to this neural network. So it applies a fully connected layer with appropriate output size. In our case, it's just one, because number of features are just one, which will result in an output tensor of shape, batch size into number of steps. Okay, so the result of every step will basically becomes the number of instances. Okay, okay, and then at this point of time, we could do the reshape again and break down these rows, the outcome here, into something like this. All right, so we could again break it back into this kind of parallel units, saying take these three, put it here, next three, put it here, next three, put it here, next three, put it here. So like that. Okay, so earlier we concatenated the result from all the sequences, then we are separating it. Okay, so all right, so yeah, we're going to walk through this. So we'll first revert to the basic cell without output projection wrapper, and then we will stack all the outputs using the reshape and apply fully connected layer without using any activation function. This is just projection. And finally, unstack all the outputs again using reshape. Okay, so reshape is the one which is going to change the dimensions and so on, right? Converting columns into rows and so on. Let's go ahead with our code. Let's just walk through the code here. All right. So here we are. All right. I think it's a time for a break. All right. Great. So far, what we have learned is that we can use RNN to do the predictions. We did the stock predictions. Then we further created something called output projection wrapper, in which we were basically converting the outcome of each cell from all the all the neurons into a single value. Then we created another network whereby that we were creating the network whereby we were basically connecting the outcome of every cell into a fully connected neurons, fully connected neural network. So let's get started. Here we have X, Y, then we created a basic cell, then we have a dynamic RNN. Okay, so this is where everything up to here is same. Okay, so here number of output we want is 1 and learning rate is something. Okay, so we'll see what it means. We basically feed this learning rate to the optimizer. Here, the outputs are RNN outputs will be converted into the stacked RNN outputs by reshaping it, and such that there is only one record per mm, one. There is only so this means that it will become two-dimensional. It will become two-dimensional, and having only one column and that two dedicated for the single value. So that's what we're doing. We are reshaping it into a singular array, into a array of single value. That's what we're doing here. So this is stacked output, and then we created here a deep neural network with these, right? So this is fully connected unit. This is a fully connected unit. Instead of using fully connected, we are using dense. Okay, this one will be having its own weights and biases and so on, and this will be the outputs, and then this. Okay, all right. So a question from Abinta is, can you show how reshape this work here? All right. So let's here at this point of time, it'll be difficult. So a easier thing would be to demonstrate here. Okay, because this one with this one will have to feed X and then see the outcome, right? Okay, so can we just use the session? All right, so I'm just using the session, and then we are saying, okay, session dot run. Okay, let's see this. Let's see if it works. So here we are going to just run the RNN outputs. Okay, and then see how it looks like. Okay. Take a look at this one and number steps. Let's say, what were the number steps? Okay. So what does it say? cannot use the default session to execute operation. The operation graph is different from the sessions graph. All right, let's just do it again. Reset graph. Okay, so we have executed this. So you can see here the one thing I wanted to show you is the RNN. What we have done is, since these are through TensorFlow, so we'll have to run them through TensorFlow. So we have fed the RNN input. We have um, created the dynamic RNN to which we have fed some value, and it has given us some result. Okay, it has given us some result. What does that result look like? Okay, what does that result look like? Let's take a look. So how many instances were there? So 50, right? So the 50 was batch size. That is the total number of instances in this are 50. Okay. Next is in each batch, because of each batch, we are getting 20 steps. So we have 20 steps as the output. Why? Because this is a network with 20 sequences. Correct? Let's take a look at further. So total number of steps we are getting is 20. Now in each of the steps, you have 100 outcomes, right? You have 100 outcomes. So it is how many, what is the value of it? Okay, so I think I'll just put it this way. Okay, so you can actually check it using an R shape, all right? Okay, so you have this one, RNN outputs are of the shape 50 instances, correct? For each instance, we have 20 sequential steps, right? So this is what's happening. So we have 50, we basically, this whole thing is a single instance. And out of this, each one is giving, these are how many steps? These are 20 steps. So these are 1, 2, 3 up to 20. And each one is giving 100 values. Okay. That is, each one is giving 100 values. Okay. Now, I hope this is clear to you. So now we can do a reshape. We can do a reshape this one. All right, where is the reshape? The, okay, and if we were basically doing it from here, okay. So at this point, um, we have just computed only the RNN outputs. We could actually compute the stacked RNN outputs as well. Okay. All right. I hope this is clear to you. And you could say we'll have to reset the graph and start from the beginning. Okay. So all right. Let's take a look at the shape of this one. So they're going to be 50 more instances. So all these values will get combined, and all right. So you can see. So for each sequence, and for all these values have been combined. So there are 1,000 such values and 100. Right? I hope this is clear to you. So the outcome of all 100 neurons is what we have as the second dimension. And this is for each batch and for each sequence we have combined together. Does it make sense to you? So you could try by yourself the similar code. Okay. And is this what you wanted to understand? All right. Okay. So why I'm deviating into giving you the details? Because the truth is that this is where we have the most confusions. Okay. With the questions which Vidya is asking, those are the main causes of confusions. And therefore, it's important to probe and experiment and run it in parts. So what I just demonstrated is that we could run it till here, then we could run it till here, and then see the outcome. And it's not necessarily always to run the optimizer and so on. So you could run the graph to up to whatever you wanted. Also try experimenting with passing the multiple here, mm, multiple operations, and then you will get the results. So try experimenting there, and let me just go back and I'll just delete this part, right? Okay, or just mark it as commented. All right, I'll just mark it. I'll just, okay. All right. Yeah. So okay. All right. I think the visual presentation of what you is this. When we are reshaping, this is what we are doing. How many dimensions does it have? There are, each instance has certain outcome, and there are so many instances. So this is basically 3 dimension, and this one is converted into 2 dimension, right? One dimension is the total number of neurons in each, and other dimension is total number of instances of such one, as in total number of records, total number of outputs. Okay, so this reshape -1 means that reshape the entire values. Okay, so how should I better describe it? Okay, I see. I see. I got you where what you mean. Here, here first we reshaped it into 2 dimension like this. Now, after this point, we will again do a reverse of this one. That's where we are converting it into back into 3 dimension. So here, so we are going to, here we converted, if you take a look at this one we have converted into from 3 dimension to 2 dimension by combining all the batches and sequences, by combining the instance and the sequences. And once we are done with all of the work, this one is going to be 2 dimensional. Then we are converting it back into these number of steps and outputs. Okay, we are doing the reverse of this one here. All right, is essentially the reverse of this one. All right, so here there are 100 neurons here as the columns. Those are getting converted into a single output, single column, and then that one is getting converted here. So essentially this is 100, right? The width of this one is 100, height of this one is number of instances, number of batch size in the instance, and so on. So I think this diagram is now clear. Is there any confusion on this? The output is 3 dimensionally. Okay. All right. Yeah. Stacked RNN output is two-dimensional. This one is two-dimensional, as we saw earlier. This one is two-dimensional, and this one is three-dimensional. Okay. So we converted this one. So this input, the input that we're feeding is three-dimensional. The output of the RNN is three-dimensional, and then we are reshaping it into two-dimensional, and then again we are again changing it to three-dimensional. Okay, just that the third dimension is a single value. Just that the third dimension here is single value. That's all. Had there been more features, then it could have been three dimension. All right. So yeah, a question is, all right, is output two-dimensional? Is output two-dimensional? Yes. This one here at this point, this is two-dimensional. That's right. So yes. So this, the one that you see here again is two-dimensional. So till here it was two-dimensional. Then we reshaped it into three-dimension. Okay. We reshaped it into three-dimension. So this one outputs is three-dimension because you can see we are changing it into three-dimension. It means that convert these values into these three dimensions such that the first dimension size is this much, second dimension size is this much, and remaining values will be in the third dimension. Okay. It's like you have a lot of values and you want to arrange them on in rows and columns, right? So first you arrange them in these three columns, then these many rows, and then you start putting the layers of this on top of this one. That's what it means. Okay. This one we are not restricting. That's what is happening. So given any data, you could always reshape it into whatever way you want it. All right. The stacked RNN outputs is this one is two-dimensional. Okay, so I will change it here. Okay, so this is output says three-dimensional. Okay, and this one is all right. Is it clear? Sorry, what I'm talking about. So this one is output says 3D. This is 2D. Sorry, this one is 2D. This is 3D. Okay. All right. Should we move ahead? Great. This one is 2D, yes. All right, so moving ahead, this way we have, let's just run the entire graph. All right. Okay, so we have y predicted value. Okay, so you can see. All right, so we were able to predict the time series. Okay, and I think the accuracy was maybe a little better than with output projection wrapper. Here the accuracy was this much, 0.04235. I think the same accuracy we achieved there also. There the accuracy was better. With output projection wrapper, the accuracy was better. All right, so moving ahead. All right, so we did this implementation. Okay, now, great, great. So now let's use our model to generate some creative sequences. Okay, so all we need to provide is the seed sequence containing n steps full of zeros. Like we could keep on feeding some values to this, and we can keep on observing the outcome. So we can use this model to predict the next value and append this predicted value to the sequence. And based on that, we can further, based on its predicted value, we could feed it back and then see the result. So this is basically called creational neural network, as in these are creative neural network whereby once they are trained, they can be used to generate the pattern, generate various kinds of things. So such as, let's say we trained our neural network on say music, right? We've kept on feeding it tunes that after C sharp it comes D and so on. So we kept on if we kept on feeding it all the music, all kinds of music to it, and the chances are that once it is fully trained, we could feed it some initial seed sequence, and then it'll start generating the music. Okay, so this is how it generate the seed sequences. So I'll just share with you. Okay. All right. Oh, somehow it was not shared with anybody. All right, are you able to access the slides? So we can utilize these kind of models to do the creative work, to create next sequences without even feeding any input. Let's take a look how creative it is. So first of all, we are going to just reload or restore the same model, and then we're going to just feed zeros to it. This means that zeros 20 times. Okay, and then we are going to run or generate 300 outcomes based on this. Okay, so this is what we are doing. All right, so let's take a look at the values first of all. So sequence is, what is sequence? And so sequence was 000, and then we appended the newly generated value to it, and then we kept on doing it again and again. So we started with 0, and then whatever outcome came here, we kept on appending it, and we kept on feeding it same thing. Okay, so it basically, the way it is that it's we trained it on a lot of music, then it started with playing whatever came into mind, and then whatever was the outcome, it again fed there. So based on the previous tune, it's basically predicting the next tune, and so on, right? So it's exactly the way we try to, if we do some kind of creativity, we just start with some blank slate, we and and we just uh, put the initial stroke, and then based on the initial stroke we do the next stroke and next stroke and so on. That's what is happening here. Okay, so whether music, whether paint, whether drawing, whether here the patterns in the stock market, so it's basically is capable of creating new sequences. All right, so you can see that based on what we have fed to it, this is how it looks like. Okay, so okay, question is what? Okay, so this one is clear, right? This one we are restoring, then this is our list of zeros, then we are going in iteration 300 times. Then here we are just picking last n number of steps from this sequence. Okay, so at any point of time, let's say we have an array A. We have an array A with 1, 2, 3. Okay, and we want to say -1, right? So we'll get last one record. If we say -2, right? We'll say, let's say A -2, we'll get last two records. Sorry, second from the last. If we start from here and say like this, let's see what happens. So yeah, so this way you can get last n number of records. So from here, if I want, say, last 3 records, so it is. All right, so this is what we are doing here, and then we are reshaping it. We are reshaping it to make it 3-dimensional. Okay, because the data that we need to feed is going to be a number of instances, bed size, then steps, and the last dimension. So then we predict it. After predicting, we again append to the sequence. All right. And here we are saying that after prediction, since it's going to be a 3-dimensional vector, so we are saying that give me the 0th record, give me the last one out of it, okay, and give me the 0th value out of it. So that way we are just appending the predicted value. Okay, we are appending the predicted value, and yeah. So basically the way here it is working is we fed zeros to it and it gave us this. Okay, and we can further make it sophisticated. Okay, by okay. Can you explain all parameters of reshape? Definitely, I can do that. So here, right? So let me just show you what it means. Okay, so I hope this is clear to you. This is clear that we are taking 0 values and it is becoming. Okay, so I'll just show you this part here. can see it's an array of zeros. All right. Then we are saying give me sequence number of steps, and meaning give me the last n steps. We're picking the last n steps. Okay. We are converting into the NumPy array. This is NumPy array, converted into NumPy array. And then we said reshape it. Okay. Reshape it. Reshape into this dimension. Okay. What does it mean? It'll basically convert it into convert it into this kind of thing. So it took all the zeros. So it first created one-dimensional vectors. Then for how many times? 20 times the number of steps times. And then it basically created the remaining as the one instance. Okay. So even if we did -1, we'll get the same results. Okay. So we are saying that take a row of values, and arrange them in these dimensions. The first dimension is 1, second dimension is 20, and third dimension is whatever is possible. Okay. So with reshape, we could rearrange any values into any other dimensions. All right. Okay. So this is 3D, yes. This one is 3D. Okay. This one is a 3D array. All right. So here we are basically reshaping this into 3D. So these are all 3 dimensions. So if you want to reshape something into more dimension than that, let's say I want to reshape it into 5,4. Okay. So we can do that as well. So basically total number of elements are going to be 5,4 into 1 and the remaining in this one. All right. So we could, this one is a 4D array. This one is a 4D array. So in if you want to convert something into let's say a single dimension array, so this should work. Okay. So this one converts anything into a single dimension array. All right. So all right. So how can I give you a better outcome? All right. Imagine that we have to arrange a set of values. Let's say these are our values. Okay. These are our values, and we have to arrange them in a rectangular formation. So we are saying let this be -1, meaning any size. Okay. And let this be, say, 3. Okay. So we are saying reshape here. We are calling reshape with -1 and 3. Okay. This is what we're doing. So what does it mean? We'll take one value out of it. Okay. So put here 1, 2, 3. So these 3 we have put there, and then the last one. Okay. This one has gone there. Okay, this is what it means by reshaping a single array into 2-dimension. So this is part of NumPy, as well as these same functionalities are part of TF also, TensorFlow also. The one that we used earlier were TensorFlow features. Okay, we used tf.reshape. Okay. Great. All right, I hope this diagram is clear to everyone. Yes, tf.reshape and np.reshape behave same way, just that if your wherever is your data, that's the one you should use. If your array is on the Python side, then you should do np.reshape. If your array is on TensorFlow side, then you should use tf.reshape. Now, that's a very important part because the reason why TensorFlow has this kind of lazy architecture is so that we could do algebra on it. Also, we could do we could do the computation without serializing or deserializing it. Okay, because if let's say you bring an array from TensorFlow side to NumPy side, that means bringing the array from the C++ side, TensorFlow is written in C++, and from that side to the Python side, that would be really inefficient. All right. Great. Moving ahead. So the creative RNN would create this kind of pattern. And if we this one is without seeding, without putting any seed sequence. This one is we just by feeding zeros as seed sequence. This is that outcome. This one is the outcome when we put the actual instance there. But after a while, it also becomes kind of plain. So all right. So you can see. So we were able to create the sequence without any input data. All right. So you could try experimenting with it with music or with any other form of input that you plan to do. All right. All right. Now let's get started. Let's move on to the deep RNN. So it's quite common to stack multiple layers of cell. It gives you a deep RNN. You can you can basically chain the deep neural network. You can say this is inside. This is basically an individual cell that contains multiple neuron. So earlier when there was one neuron, we generally used to call this as neuron, but this is essentially a cell. The cell is the one that feeds it back, and there could be multiple neurons here. Now we could stack such kind of cells, and that's what is known as deep RNN. Okay, so deep RNN, if you unroll that through the time, this is how they will look. So at time t equals 0, we are feeding something here. It's giving some output. Then the output of this is going to the next step as well as to the next cell. The next cell is giving again the same thing. And at time equals t1, the next time step, then the values from the previous one are fed to each of the cells along with the inputs. So this is what a deep RNN looks like. How to implement deep RNN in TensorFlow? So to implement a deep RNN in TensorFlow, we can create several cells and stack them into a multi-RNN cell. Okay, if you want to implement deep RNN in TensorFlow, we can create several cells and stack them into a multi-RNN cell. In the following code, we stack 3 identical cells. Okay, so all right, so we have right? So to implement a deep RNN in TensorFlow, we can create several cells and stack them in multiple RNN. It's a simple way using we create the basic one just like we did earlier, and then we call multi RNN cell. So that basically create the structure, how many ever layers we want to specify, and then we using dynamic RNN we could create the neural network. Okay, so here if you want 3 layers, you just multiply this with 3 layers and so on. Okay, so same one, we're basically passing an array of the basic cells. We're passing the array of basic cells here, and yeah, or you can say vector of basic cell is being combined to form a deep RNN. A question from Binda is, does each step have the same amount of cells? Okay, a good question. So yes, basically all the 3 are identical cells in this one. Okay, in this one there are all the 3 are identical. Okay, so the cells, all of the 3 are going to have equal number of neurons. All the 3 are going to be, if you, this one has 10, this one has 10, this one will have 10 as well as this one. So all the 3 are going to be equal number of neurons. All right. So when we call dynamic RNN, we are going to get outputs as well as states. Now, the states variable is a tuple containing one tensor per layer, each representing the final state of the layer's cell with the shape, bed size, and number of neurons. Okay, so the states variable here is a tuple containing one tensor per layer, each representing the final state of that layer's cell with shape. Okay, now if you set state underscore is tuple as false when creating multi RNN cell, then state becomes a single tensor containing the states from every layer concatenated along the column axis. So we can basically here we will get the output. We'll get the output from each of the layer, and along with now, here the states will give us the output from each of the layer. All right, same is the case with outputs. All right, so if we build a very deep RNN, it may end up overfitting the training set. Again, to prevent the overfitting, the easiest one is called, a most common technique is called dropout. You can simply add a dropout layer before or after RNN as usual, but if you also want to apply dropout between RNN layers, you can use a dropout wrapper. Okay, dropout wrapper around the basic cell. Okay, say for example here, we created a basic RNN cell, then we wrapped it in a dropout wrapper, then we wrapped it in a multi RNN cell, or we created the multi RNN, the whole stack, and then we created the dynamic RNN. All right. So dynamic RNN is the one that does the magic while the first construction is done by the cells. Okay, so it is also possible to apply dropout to the outputs by setting output underscore keep underscore prob. The main problem with this code is that it will apply dropout not only during training but also during testing. All right, which is not what we want, since dropout should be applied only during training. Okay, so we could pass there is a variable called output underscore keep underscore probability, that we can pass. If we pass at 0.5, that means we want a dropout of 0.5. But then every time we run the network, we will always have a 50% dropout, irrespective of whether we are testing or training. In both the cases, we will have the dropout. So it's better to create your own wrapper. Okay. So dropout wrapper does not have is training placeholder. So either we must write our own dropout wra- wrapper class or have two different graphs, one for training and other for testing. That's also possible that we create that's also possible that we create two two separate workflows, one for training and other for testing. Dur during training, we can uh, the easiest option generally is that we could just clone the code and then use it. All right. Generally, as when it comes to when it this is a common question that you will face, that that how does the testing happen, right? How does the prediction happen? And so training is done generally on different machines and predictions on different. Say, for example, you want to do certain prediction on mobile, and mobile does not have that capability of running so many layers, right? So many a times you don't have this option of making a call to the server and get the results, get the server do the prediction. Sometimes you might have to do the prediction on the phone itself, right? In that case, what you have to do is you have to write a separate program in TensorFlow, which can run on the mobile, which can load the same model that you generated on the server side and do the prediction on the mobile. So basically, it's also common to have two different graphs, one for training and other for testing. Okay, so all right, not only for the dropout or regularization, but also for the technical perspective, whereby the requirement is that the RNNs are going to be, or your neural network is going to be running on different machines. Okay, training on one machine and running on different. It's very common. All right, so. Okay, so here we go, and we have X is placeholder, Y is placeholder, that's usual one. Then we created the basic RNN. Then if it is training, then do this. Okay, if it's training, then we have the dropout wrapper. Okay, and then we have multi RNN cell as usual. And in both the cases, here we are passing cell and here passing cell. Notice that this is also called cell, this is also called cell. Okay, so essentially we are, if it is training, then this line comes into effect. Otherwise, if it is not training, then this line is skipped, which is dropout. That's correct. That's correct, Binda. All right. Then we have, let's just go to the, yeah. Okay, so this is where we are. We talked about multi-RNN already. Okay, so let's take a look. All right, so here you can see that dropout wrapper, the usual one, has something called input key probabilities. This can be used for basically applying the regularization. Okay, and here you can pass, like, say, drop by 50% and so. And we have here, all right, so one way could be this one. Okay, the other way could be using the is training is training variable. Okay, where is training variable here? All right. All right. So that one is not mentioned here. Okay, it's not mentioned, but it should be very straightforward. All we need to do is we create this is training equals this, and we are taking this as argument from the in the program, and we are saying is training equals this, and so on. So yeah, so that one we can use. Okay, so all right. Also, you notice the other changes like if is training, then we run the initialization variable, and then do the iteration. And otherwise, we just do the restore and do the evaluation of the input data. Okay. So one is for running it, other is for training it. So we could this is a more common this is a more common approach as compared to the other one. All right. All right. So there are some right. All right. So we can apply dropout. We can apply dropout either with using the dropout wrapper. Okay. We could also create our own wrapper, but using dropout layer is exactly what we would do. And in that we can pass the key probability, how much percentage of the uh, neurons you want to retain. Generally, we pass it as 0.5, right? So and dropout helps us in regularization, and that's why we use dropout. Now, next is there are difficulties of training the deep RNNs over many steps. To train any RNN on long sequence, you will need to run it over many steps, right? Making the unrolled RNN a very deep network, right? Just like any deep neural network, it may also suffer from vanishing gradients. Why? If you take a look at our previous um, one, okay, so where was it? I'll just try to, okay, not here, not here. Okay, so yeah, let's take a look at this one. Imagine that this is our neural network with multiple, this is our RNN with multiple steps, correct? So let's say this is our output and we want to optimize we want to tweak the weights. So first we have to compute this error with respect to this with respect to this with respect to this with respect to this and this, right? And so eventually what will happen is the weights will have to multiply all of this. Okay. We have to multiply because of the chain rule, we'll have to multiply all of these, and hence we might end up with vanishing gradient problem. Okay. We might end up with either vanishing gradient problem or exploding gradients. So many of the tricks that we discussed earlier to alleviate the problems were same as the deep neural network. Like we could we so we could apply the same thing that we learned earlier for the fully connected or dense neural networks. One is having a good parameter initialization, such as HE initialization. Next is good activation function, such as ReLU. The third one is doing the normalization using, say, batch normalization. Next is, say, for avoiding the gradient explosion, we could have the gradient clipping. And we could use, of course, the faster optimizers. And as a thumb rule, everybody uses the Adam optimizer. All right. So if the RNNs needs to handle even moderately large sequence, say 100 inputs, 100 sequences, then training will still be slow. The simplest and the most common solution to this problem is to unroll the RNN only over a limited number of time steps during training. Okay, so the most common solution is that don't keep the RNN sequence too big. Okay, and we generally call it the truncated backpropagation through time. All right, so in TensorFlow, you can implement truncated backpropagation through time by simply truncating the input sequence. Okay, for example, in the time series prediction problem, you would reduce the number of steps. Instead of having 20, you could just decrease it to 10. All right, but 20 is completely okay. The problem with this is that the model will not be able to learn long-term patterns. All right. So the only problem with if we keep on decreasing, the number of steps, then it may not be as robust as the one with the bigger sequence is. Okay. Then how do we solve such a problem? So one of the workaround could be to make sure that these shortened sequence contain both old and recent data, right? So that the model can learn to use both. Example, the sequence could contain monthly data for last 5 months, then weekly data for last few weeks, and then daily data for last 5 days. But this workaround has limits. What if a fine-grained data from last year is actually useful? What if there was a brief but significant event that absolutely must be taken into account, even years later? So say for example, the results of an election. The election happens after, say, 5 years, and therefore, if we are ignoring the data that was 5 years ago, then that would not be that would be a mistake. Specifically, let's say you are observing the impact of an election on the stock prices, right? Now, since the election happens, say in the countries like India, the election happens, say, 5 years, and and there if we are ignoring the inputs of 5 years ago, then we may not get the correct results, right? Maybe the fine-grained data, like exactly 3 days after the election, such and such thing happened. Okay, so in those cases, we might have to have a longer sequence of the RNNs, which may be difficult to train because it will be really complex. All right. Now, the other problem is, beside the long-term training time, the the other problem is the fact that the memory of the first input gradually fades away. Indeed, during the transformations that the data goes through when traversed through RNN, some information is lost after each step. Okay. After a while, the RNNs contain virtually no trace of the first inputs. Let's understand this with an example. Say you want to perform the sentiment analysis on a long review that starts with 4 words. I loved this movie. And but the rest of the review lists many things that could have made the movie even better, and so on. If the RNN gradually forgets the first 4 words, it'll completely misinterpret the review. To solve this problem, various types of cells with long-term memory have been introduced. They have proved to be successful that basic cells are no longer in use. All right, let's learn about long memory cells. The first one is LSTM. LSTM was proposed in 1973 by SAP and Jurgen, and it was gradually improved over the years by various researchers. All right. So if you consider the LSTM cell as a black box, it can be used very much like basic cell. Even if you don't understand LSTM, you can just use it. But it's actually pretty easy to visualize it because it is basically like our usual workflows. Okay. So it performs much better. Training will converge faster, and it detects long-term dependencies of the data. All right, you can just use basic LSTM cell. LSTM cell manages two state vectors, and for the performance reason, they are kept separate by default. We can change the default behavior by setting state is tuple equals false. All right, we can change this default behavior where having the two separate vectors by changing this particular variable. Let's talk about this architecture. So this is instead of a very simple cell, this is a little complicated cell. Okay, let's try to understand it. Here, before we jump into it, let's look at what it is. There is an input xt and single cell, single step. This is single cell, single step, and single instance. We're feeding xt. Xt might have multiple dimensions or multiple features. So we're feeding this to 4 fully connected neural networks. Okay, we're feeding this to 4 fully connected neural networks, and then the outputs are coming from this. Along with the input, there is something called ht-1 that's coming from previous step. Similarly, there is something called ct-1 that's coming from previous step. C and h are coming from previous step. And here, the h is being fed to the fully connected network along with x. Now here, this is where the multiplication of G and I is happening. This is a multiplication place or multiplication gate. And this one is a forget gate where here again there is a multiplication happening. Here there is a summation happening from both the sides. And then the output of this one is going to the next step as C. And the other one is passing through the 10H. This is 10H. 10H is the activation kind of a function, and then being multiplied with the output of the fourth one. Okay, so you can see that some of the output of the fully connected network is going directly having the most impact. Some is being merged with the second one and is basically giving to the memory. This is giving to the memory. This is also giving to the memory, and this one is taking memory, and so on. All right. So this is the architecture of the basic RL. Okay. So we can think of HT as the short-term memory and CT as the long-term memory. This is short-term memory. This is long-term memory. Okay. Because short-term memory is revamping a lot, whilst the long-term is being retained. A question from Binta is, we have two activation functions chosen here. Yes. So this is 110H. The activation for all of these is different. This is here the activation as logistic, and this is also logistic. This one is 10H and this one is 10H. Okay. So the key idea in this network is that what to store in long-term state and what to throw away and what to read from it. Okay. So there is a forget gate. So as the long-term state CT-1 traverses the network from left to right, it first goes through forget gate and dropping some of the memories, and then it adds some new memories via the addition operation, which adds the memory that were selected by an input gate. Okay. Okay. So here is basically adding to the memory. So the result here, the result is being sent out directly from here after addition of some more memory. And so at each timestamp, some memories are dropped and some memories are added. Moreover, after the addition operation, the long-term state is copied and passed through 10H, and then the result is filtered by the output gate. Okay, and then the result is filtered by the output gate. All right. Now this produces the short-term as well as the long-term memory, as well as the output. So whatever is whatever is going as the short-term memory is the same as output. Okay. So it's like thinking slow, thinking fast move book, whereby you have long-term memory and as well as short-term memory. In the same way here also, the idea is that there is something called instinct and there is something called gut instinct, and there's something called reaction, right? So short-term memory is the one that you can say that it's a quick recall, while a quick recall, and this one is a long-term. Okay, so it basically balances between the two. Now let's take a look at where new memories come and how the gates work. First, the current input vector xt and the previous short-term state is fed to 4 different connected layers. They serve a different purpose. The main layer is the one that outputs GT. It has the usual role of analyzing the current input xt and the previous short-term memory. In an LSTM cell, this layer's output is partially stored in the long-term state. Okay. Now the three other gates, the three other layers are gate controllers since they use the logistic activation function. Their outputs range from 0 to 1. Now, whatever is here is represented here. Okay, whatever is here is represented here. I is a function of x with the weights multiplied to it and ht minus 1 and so on. So I, f, and o are similar. They have different weights and biases. These are different weights and biases. Along with there is an activation function. In case of the I, f, and this is o, right? What's this? Yeah, it's O. So I, F, and O are exactly identical, in which the previous steps, the short-term memory is mixed with current and with biases. And this one is very similar to the others. The only difference is the 10H. And then we have, right? Then we have, we are basically doing multiplication. So we are doing cross multiplication here. And this is called element-wise multiplication. Okay, and so on. So we are multiplying sum of C, so C with FT, sum of C with FT, and then adding it with multiplication of GNI. Okay, and so on. So basically, this is what an LSTM looks like. Okay. A question from Bintao is, what does element-wise multiplication mean? Multiplication is this, okay? I'll just show you what does it mean by element-wise multiplication. Let's say you have two vectors. You have, let's say, x, y, z, and you are doing element-wise multiplications. So you have, say, a, B, and C. You multiply x with A, y with B, and so on. So answer will be XA, YB, and ZC. That's what it means by element-wise multiplication. It's not like your dot product. Okay. So LSTM can learn to recognize an important input. That's the role of the input gate. Store it in the long-term state. learn to preserve it for as long as it's needed. There's the role of forget gate, and learn to extract it whenever needed. This explains why there have been amazingly successful, why LSTMs have been amazingly successful at capturing long time patterns in time series, long text, audio recordings, and more. In basic LSTM cell, the gate controllers can look only at the input X and the previous short-term state H. It may be a good idea to give them a bit more context by letting them peak at long term. So there was a minor modification by 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 Felix and Jürgen in 2000, and they proposed the peephole connections. The peephole connections are nothing but one connection goes from here to here and from here to here. That's the extra connection that you get. Okay, so one of the inputs is fed here, one of the inputs is fed here. All right, so all you need to do is you just need to say use peephole instead of with LSTM cell. Okay, so that's all. With the LSTM, we can in the similar way we have GRU cell. GRU cell has the similar kind of architecture. It is far more simpler, and the both basically it's both the extremely simplified version of GRU cell. So all right, so that's pretty much for today. Or can we take some more time, because we have still 2 chapters to finish and we are left with 2 sessions. All right, so can we take like 1 extra hour tomorrow and next day? Tomorrow and next Saturday, next Friday for you. All right, so should I proceed to explain what is GRU cell? Essentially, GRU cell is okay. So the main simplifications here are basically we have removed like multiple fully connected network from here, and both the state vectors H and C, long term and short term, are merged into one, and a single gate controller controls both the forget and the input gate. If the gate controller outputs a 1, the input gate is open and the forget gate is closed. Okay, so basically this one is the kind of valve whereby this controls whether this output goes here or this output goes here. So that's the main part of the GRU cell. And if the output of this one is, so basically it is switching between these, whether this would go here or here. That's the core idea. So this is where it is. So this is where it's switching between W into H and Z into ZT, Z into this one, right? This is that, okay, GT is this value. Here at this point of time, this is called GT, whether to multiply this with this output or multiply this with this. That's the switch that is happening here. And this switch happens with this value called ZT. Okay. So basically this switching is happening here. That's the main part of the GRU cell. Okay, so it's basically the similar neural network with little bit more complex structure. All right, so GRU cell is you can just use GRU cell out of the box, and generally in the production environment or in any of the predictions, you will either use LSTM or GRU cell, and the both of these perform really well. Okay, so GRU cell is simplified. GRU cell is simplified while LSTM is more complex, and GRU cell is GRUCell is essentially uh, for the cases when you can't use LSTM because of the overhead. Okay. A question is there a long-term memory with GRUCell? GRUCell only has same memory. There is no difference between long-term and short-term. This is the one that is called their long-term memory, HT. Okay. So one copy of it is fed to the actual neural network. Okay. And the other copy is multiplied with the outputs of these. Okay. That's what is happening here. So that's the reason that's you can use GRUCell out of the box. There is no way to prove that why there is no way to deduce that this is how we can reach to GRUCell. It is more of experimentation and a bit of instinct that has led to these researches. All right. So these RNNs also have a big application in NLP. So we'll talk about NLP tomorrow. We'll start from here. We'll talk about word to vec and sequence to sequence tutorials. And those who want to be prepared for tomorrow's session, I would strongly recommend these two links from Google. These are actually really well done tutorials from TensorFlow. Okay. All right. So before the tomorrow session, please go through these two links. It'll be useful, right? Because I'm going to go through their tutorials in the tomorrow session. All right. We'll continue from NLP tomorrow. All right. Thank you, everyone. I look forward to see you tomorrow. Bye-bye. Have a good day.